So welcome back to our lecture on the components of deep learning. There was a question. So linear regression uses the squared error loss. And what about logistic regression? What loss does it use? Logistic regression uses the logistic loss, which is also called binary cross entropy loss. You can read more about loss functions in chapter 2 of my machine learning book. I'll post the link again. So then another question, what was the term for the combination of model plus loss function? I don't use a specific term for that. I think sometimes authors use the term model to also include the loss function. But as I said, I use a very strict definition or strict use of the word model. It's just a set of different hypothesis maps. And you can use different loss functions to search or to kind of rank or score these hypothesis maps. But sometimes some authors include the loss in when they say model. When they say linear model, they implicitly mean squared error loss. However, you can use other loss functions to learn a linear map, even in regression. So does any one of you know of another loss function that can be used to learn a linear hypothesis for predicting numeric labels? MAD, yes. What's the name of MAD? When you spell it out? Mean absolute deviation, or the average absolute loss. So the squared error, when you look at a data point having, maybe I go now over to my sketchbook. Yeah, by the way, I will then share these handwritten notes with you on the course page. They are not there yet because I do them now live. It's not ready-made, kind of freshly cooked. So when you look at a data point having a numeric label, y, for example, might be 3.2. And you want to predict the label just from the features. Let's say we have a feature vector x, which consists of 5 individual features. So we can use a linear model, which is a linear map. We take the inner product of a weight vector with x and get a prediction. So we call this is we use this as a predicted label. So this is the predicted label. Predicted label. So, and one option to measure the quality of this prediction is use the squared error loss, which is this. This is the squared error loss. And another option, equally valid, is the absolute error loss. Which is y hat minus y absolute value. Okay. So do you think, is it always clear which loss function to use when you look at, when you get some data and you have to predict a label? How would you decide which loss function to use? Like, when would you use the squared error loss and when would you use the absolute error loss? Very good comments here. If it has outliers, so if the data contains outliers, you would rather use the absolute error loss. Yes, because if you look at the data set, so let's say we have some training data. Here we have a feature and here the label. And so we have some training data points for which we know the label. Otherwise, I could not draw it, because if I don't know the label value, I cannot locate a data point on the vertical axis. And let's say we want to fit a linear predictor to this. So then it would be nice if this linear predictor, if the machine learning method that chooses a linear map to predict the label, is not kind of messed up if we have one data point which is completely off. So it would be here. And this we call outlier. So a data point which has very different properties or which behaves fundamentally different than the majority of people. So majority of data points, sorry, that's called an outlier. So we would like a method to be not too much dependent on outlier, or basically ignore outliers. And it turns out that if you use the squared error loss, then an outlier will pull away, will completely mess up the learned hypothesis. So you will end up with the green hypothesis instead of the red one. Whereas if you use the absolute error loss to measure the quality of this predictor, you will only get a small perturbation. So the hypothesis, the learned hypothesis, will almost be completely ignoring the outlier. This is what you typically want, a robustness against outliers. So this absolute error loss can offer to some degree a robustness against outliers. So it seems we should always use the absolute error loss, or it's always good to be immune to outliers. Why should we use the squared error loss then? We don't want to be vulnerable against outliers, in machine learning here at least. Anybody defending the squared error loss, which is, I guess, the most widely used first choice for a loss function when you predict numeric labels? Why are we using the squared error loss? Yeah, so if we remove the outliers, then this argument falls away. Yeah, the error can be negative and positive also for the absolute error loss. Also, the absolute error loss can handle this. Yeah, the squared error loss has a nice interpretation of being the optimal estimator from a probabilistic perspective when the noise is Gaussian, but who knows if the noise is Gaussian. So we want really this robustness against outliers, let's say, is very important for us. There's one good comment, more efficient. Yeah, in which sense more efficient? In which sense could the squared error loss be more efficient? At least it's not more efficient regarding tolerance to outliers. So this is not the efficiency of squared error loss. But what? Yes, during optimization, it is easier to fit. Yes, in which sense easier to fit? We can use gradient descent, yes. So this brings me now maybe to the last and final conceptual component of today's lecture. So let's now bring this all these components together. So we have some training data. We have a set of hypotheses, and let's say we have a parameterized set of hypotheses. And this is what we mostly use, or what we always use in deep learning. Deep learning uses parameterized sets. So each possible hypothesis map can be identified, or like an ID, like every one of us has a Kela ID. So each hypothesis in deep learning has an ID in the form of a long sequence of weights. So this one has weight 0.1, 2, 2, 0, blah, 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 blah. And deep learning method use millions or even billions of such individual weights, and the whole sequence of these weights, which, by the way, we typically also store in a NumPy array. This whole sequence of weights identifies one hypothesis, one possible hypothesis. And here, this green one has another ID or another weight vector. So here the weight vector would be, let's say, 1, -1, 3, blah, 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 blah. So each hypothesis is identified by one weight vector. So, and what we can now do is we can draw an objective function. We can draw a function, the loss or the average loss. So we typically average the individual losses over all training data points. So we do 1 over m, where m is the training size. And we average the loss for the ith training data point. And we average over all losses. So you can find more details. Don't worry if this is too fast for you. You can find all the details in the course book as indicated on my courses. So, or let's say the average loss, or training error. We call this also training error. And we vary, so we look at how the training error varies with respect to the weights. So we tune the weights. This is what we tune, and this is what we also tune in deep learning, in the deep learning methods. We tune the weights. So, and we want to find the sweet spot here. So here we are happy because we have, this corresponds to the minimum training error. Minimum training error. And how do we find this optimum? Well, we have to optimize the function. So machine learning or deep learning methods are nothing but a special case of optimization methods. So the more you know about optimization methods, the more you know about deep learning. So we start with an initial guess for the weight vector. Let's say all weights equal to 0 or all weights randomly chosen. And what we like to do is we want to find a better choice for the weights. So how can we do that? Well, it seems natural to go downhill, so to go down the gradient. And this gradient here, so let's call this average loss function f of w. So this f of w is just this average loss. So we go down the gradient. We go in the direction of the opposite direction of the gradient. So we go down the gradient and end up at the new estimate for the weights. So this W1 is W0, and then the gradient step minus alpha gradient at the first iterator. And this basic principles is used by 99.999% of all deep learning methods. That's how they learn. That's how they tune the weights of a deep neural network, going down the gradient. This might sound easy, like this couldn't be the principle of deep learning, this simple principle, but there are some challenges because computing the gradient might involve summing loss terms or summing over data points that billions of data points. So summing over billions of data points, which are stored in distributed databases all over the planet. So you need to gather data from all over the planet to actually do one evaluation of this gradient. So typically you need to approximate the gradient, and there are many different methods to approximate gradients. Maybe one of the most popular one is using stochastic approximations. And then gradient descent becomes stochastic gradient descent. But the basic idea is always the same. Go down the gradient a bit. Okay, so what we now have is in deep learning methods, we always look at the sequence of loss functions, of loss values. That's what you see in these convergence plots. So here you see the number of gradient descent steps. Sometimes we group gradient descent steps to obtain an epoch, but in the end, what the horizontal axis in this convergence plots indicates is how many steps did we do already? How many such elementary gradient descent steps did we do? So we start with 1, 2, 3. And of course, you start with a large loss. So in the beginning, when you initialize randomly, you will not make any good predictions on the training set. But you go down, 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 down. And yeah, typically the loss we use as loss function, non-negative numbers. So we can never go negative. So this is the loss on training set. But what will happen in deep learning methods, because they use such a large set of predictor maps, highly nonlinear predictor maps, they will almost for sure contain one such crazy predictor map, which perfectly goes through your training data points. So what you will see is typically in deep learning methods that this training error goes towards 0. Okay. So you will find at some point you have so many different options for choosing the weights, so many different hypothesis maps you can represent using a large neural network that you will go down to 0 or very small values for the loss. But as we already discussed, this doesn't mean much. This just means, well, you were able to search over a large hypothesis space to find one hypothesis map that almost perfectly goes through the training points. But you might have just overfit, and you typically will just overfit the training data. To avoid overfitting training data without any more advanced tricks like regularization, which we will talk about in a later round, does any one of you have an idea how many training data points we would need such that overfitting is unlikely to happen? I have talked about a lot about large models, large hypothesis spaces, but what does large mean? So large, we can, a measure of a hypothesis space could be the number of tuning parameters. And in deep neural networks, we use the weights, let's say only the weights of the connections in the neural network as tuning parameters. So we have billions of tuning parameters. And the basic rule of thumb is you should have at least better 10 times more training data points than tuning parameters. And if you have billions of tuning parameters, you should have tens of billions of labeled data points. So I guess nobody of you wants to label tens of billions of cat and dog images if they chose a cat or a dog. Nobody wants that. However, there's a workforce for this to do this. It's called Amazon Mechanical Turk, for example. You can rent labeling time there. So you can dump your image database, and for some hourly rate, somebody will label each of your image and say, okay, this is a cat image, this is no cat image. But it costs. So labeling costs, and typically you cannot afford labeling tens of billions of data points. So you will have less, let's say 100. So you spend an hour to label images and you have 100, but you train a network with billions of tunable parameters or weights on it. So what you will get is training error 0. You will perfectly fit the training data, but this doesn't mean much. So where should we go next? Or how do we know what to do? Training error is not enough. Training error just means, a small training error just means that you were able to use some gradient descent method to search over your large hypothesis space. A sensitivity analysis, yes, and this is also related to testing or validation. So always look at the test set or validation set. I somehow like the term validation set more because we typically use the validation error to do something. So we look at the error on the validation set of the hypothesis. So we have some other data points. Let's see, here one, and here one, and here one, and here one. And we train this blue curve. It perfectly fits the training points, but it incurs a large error on the validation set. So what we get is a large validation error. So this is the loss at the validation set. So what you will see typically in any deep learning Python code, right after you read in the data, you do something like splitting in the data points into two sets, a training set and a validation or a test set. This is almost in any piece of code for deep learning. You split the data into a training set that you use for tuning the parameters of the neural network. And then you use another data set called validation set or test set to evaluate the trained hypothesis. And what do we do? We would like to find, of course, the the number of gradient descent steps that minimizes the validation error. But then we might not be happy. We might not be happy because this validation error is just too large. So it might be too large. So now the cycle starts again. Now the machine learning or deep learning engineering and deep learning design starts to happen in an iterative fashion. So you have now found the optimal number of steps. So you have trained the model until it starts to overfit. So here we have overfitting. This we can then ignore, this part. And here's the truth, or here's the reasonable part. And we know that, or let's say we found that this error is too large. It doesn't do sufficient accurate predictions, the network. What would you do next? Go down, yes. With what? Go down with what? Yeah, go down the error. We want to get down the error. Yes. Change the model. Yes, that's a good idea. So it seems here for this particular case that here we don't have overfitting because the training error is at the same level as the validation error. So there's no overfitting. So this could be just that the model then doesn't have a sufficient or a suitable predictor map in its repertoire for the data at hand. So we should maybe change the model. How do we change the model in deep learning? What do you think? Use a different architecture. Like there's some architectures, a UNet, there is CNNs, there are RNNs, and so on and so forth. Different architectures. Yes. So we might look at a different architecture. Let's say we don't change the architecture. How could we change a model otherwise? When we do deep learning, what is the deep about? Layers. Add more layers. Yes, it might also be that we should change the loss function, and this is related to regularization. So we can regularize a machine learning method by, for example, not only using the squared error loss here, but adding some term that depends on the weights. So maybe one option is called enriched regression. So we use as loss not only the squared error loss, but the squared error loss plus the 2 norm squared of the weights. So using this as the loss function for training the model could help, could prevent overfitting. Yes. Yeah. Okay. So, but I would say a main tuning knob, so to say, for deep learning methods is the number of hidden layers or the number of layers. But don't worry if this ring a bell yet. Layers, we will talk about layers in the round 1, which will start, I think, next week, at least the lecture. The round 1 will explain what are layers, what are neurons, and what are artificial neural networks that represent highly nonlinear predictor maps. Okay, but I think, yeah, for today, this was a nice recap of the components of machine learning, and in particular, how they are put together. In the end, machine learning and deep learning is about searching a large model, which is a set of different hypothesis maps, such that the predictions obtained by this hypothesis yield a small loss. And they should yield a small loss on any data point, not only on the training set. If they yield a small loss only on the training set, they might perform very poor outside the training set. This is related to overfitting, and much of deep learning theory and methods go into first detecting or finding out the settings where the method will overfit most likely, and then coming up with tools or techniques to avoid overfitting. One main approach is called regularization, and this we will discuss in round 4, I think. Okay, any questions at this point? yeah, please, again, post questions, answer questions, discuss, interact with your colleagues in the Slack discussion forum. In particular, all these questions, these excellent questions that have now been posted on this Zoom chat would be ideal to also have on the Slack. Okay? If you have problems accessing the Slack, write me an email or Shamsi or Andy. And yeah, otherwise I will now do a quick post edit of the recording today. I will put the recording and the handwritten notes of this lecture on my courses by today or latest tomorrow. And yeah, otherwise I wish you a nice week. Talk to you and see you next week then. Bye.